we on? 8. Okay. In case you were not sure. What have we been talking about? Combined with material balances, right? So what my plan is we've been doing this problem, so I'm going to try and finish this problem today, and then also present to you what do you do when in this particular problem we have only one phase, what do you do when you have multiple phases, and then when you come back on, and then Monday we are going to just work on our exam questions for the exam, everything, so I'll not do anything new on Monday, okay? So I'll try and finish chapter 8 today. My hope is that between today and Monday, you will look at the test that is posted. There is a blank version posted, so I strongly suggest that you try that on your own. Especially, I would suggest that you work with the last problem on the test. The second problem, which I think was a condenser. The thing is, if you read the problem and you just look at the solution, it's very obvious how to do the problem. But a lot of people last year struggled on that problem, as your UGTLs are nodding, right? And so I would strongly suggest that you work on it yourself, because there are very small nuances to that problem, which only when you work it out on your own will you realize that, oh, this is missing, but I can just get this information from this step, etc. So that would be my only advice as you're studying for the test, okay? All right, so jumping back into this problem, what we had set up on Wednesday was this idea that you have a gas, which the composition of the gas is given to you, and it's leaving a furnace, and it rapidly cools to ambient temperature of some 60 degrees, okay? So then what we are trying to image this as is the idea that, okay, maybe something came in from a furnace, into a furnace, we don't care what, but something is leaving the furnace, and then somewhere it is being cooled and it drops to a temperature of 60 degrees. So you have 1200 Fahrenheit, and then the thing is being cooled, right? So change in temperature such that you are at 60 degrees Fahrenheit. And you have been asked how much heat is given off to the surroundings. And one of the first things I said was, well, as always, think of the sketch, and here this is kind of an approximate sketch I have drawn. And the next thing you want to think about is always the material balance problem. So we've tried and identified, we have 3 systems, 3 compositions. The compositions are written out. This is a straightforward problem where we know that if something went in at 1200 and nothing changed, what comes out has to be what went in. So that's the material balance part, and we put it right in there. And so that part of the table is set up. What I also would like you to realize here is when you're doing material and energy balance, or just energy balance, you also have to highlight that you're working with, what are these hats over here? Specific values, right? So you're working with specific values, and then you will multiply it by the composition to get the total enthalpy of the system. Now, why should I care about enthalpy when I was asked to calculate how much heat is given off in the system? How do I know how to relate the heat to the H? Right, start out with my complete energy balance, right? Now that we've done the table, let's start out with our complete energy balance. Does anyone remember what the complete energy balance looks like? You hopefully do. Otherwise, we are in trouble in the second exam, yes? Okay, so I think I wrote out everything that I needed. Yes? Okay, now in this particular problem, do I have a H? Probably, right? Because nothing has been told. Do I have a K? Energy change due to kinetic energy. Do I have a potential energy change? Do I have any work done? Is there any shafts moving the system? Even if there is, we don't know, right? So we say these are 0. This establishes for us that in order to calculate Q dot, which is what we are being asked, we really need to calculate the change in enthalpy, right? So when I say I'm calculating change in enthalpy, what am I really calculating? Would you agree that it's kind of H out minus H in times M dot? Yes? So this part we really want to remember. Now, since there is no M dot given in this particular case, we can also say, okay, we could report the answer in terms of Q dot by M dot, which is H out minus H in. So the question then becomes, from this table, how do we calculate H out and how do we calculate H in? What do you think is H out? You have three components, and I'm asking you to calculate the H out and I'm asking you to calculate the H in. Any thoughts? Okay, so H out and H in, they will all be the proportion, the composition proportion sum of these systems. What does that mean? If I say H in, that is nothing but the sum of the composition Xi, Hi hat. Is that clear? If I'm writing it this way. Because remember, when I say this, sorry, I forgot my hand here. Does this make sense to you? Why can we do this? Do you guys remember from Wednesday's lecture? Why can we do this? What's that? Conservation of energy? Ideal gas, ideal mixture. Not ideal gas, sorry. We are assuming that this is an ideal mixture. For ideal mixtures, it's a straightforward addition. In 512, we will learn how to deal with non-ideal stuff. I am going to freak out if I have to consider that right now, okay? So we will deal with just ideal system. Okay, so the same way, I will say that H out looks the same. That is the sum of Xi, Hi, but in this case, outs, okay? Now, great, I have this part done. Then from here, how do I calculate the H's then? Basically, what that means is I have to calculate H1, H2, H3, H4, H5, H6, and then multiply them by their compositions, and then I should have sums, right? So how do I calculate H1, H2, H3? We just set it up on Wednesday, so what do we remember? Yes, Nathan? Okay, you could always integrate from T1 to T2 for CPDT, but for which value? So Nathan wants to integrate, which is not a bad idea. So you want to integrate H1, yes, from T1 to T2. What are your T1 and T2? What are your T1 and T2, the two temperatures given to you? Yes? Yeah, so this is what happens, that even though it is right that T out is what is going out and T in is what is going in, that is not right. Thomas, did you have a different thing to think about?
Well, if you're just doing in out, I know you're not doing one.
What's that?
So say you do the integral thing, temperature in, temperature out. Yeah, you're not just going to solve for one of the variables.
That's
it's not H
That's right. So the reason why you can't do T1 and T2 is because, as Thomas is saying, H1 is only for the in. So you can't use both the in and the out temperature to calculate for something that is just going in. Okay, because there is a H4 out too, right? So this idea here won't work. You can still use this concept, but hold on to that thought. I will show you how to do that a little later. I want to show you the long way first, okay? So the long way to do this is calculate H1 at 1200, H2 at 1200, H3 at 1200. How do I do that? The easiest thing to do is if you could find tables, that would be wonderful. Okay, so the problem is here's a table, and over here in this table, I actually have nitrogen, which is something I was looking for, carbon dioxide, which is also something that I'm looking for, and water, which is also something I'm looking for. Now, that means I need to consider 1200, the value of nitrogen, carbon dioxide, and water. And if I do these three, that gives me H1, H2, and H3. So that means, and I'll come back here in a minute, I just want to write down, from here, I can argue that H1 is 8151, H2 is 12533, and H3 is 9831. Okay, great. So I have H1, H2, H3. I also need H4, H5, H6. Yes? Sure.
You're supposed to subtract your reference temperature from the temperature like on the chart. So you're at 1200 right now, but are you supposed to subtract like 77 from that?
Okay. Good question. So Erin wants to say, well, aren't you supposed to subtract your reference temperature from it? Any thoughts on that?
Since the table's using 77 as the reference temperature, you see that it's 0 for each of those at that temperature, which means you don't have to subtract.
Does that make sense to everyone? You identify what your reference temperature is, and here the reference temperature is 77, so then you don't have to worry about that in this particular problem. Does that make sense? Because that is your 0. Okay, and for now, any questions, concerns? One thing is, if you want, for this problem statement, I may have said degree centigrade, or was it degree Fahrenheit? It was Fahrenheit, so we are fine. So any other concerns, or is your question clear? Is your question answered, Erin? Yes? Yes? Okay. And I'm sure many others had this. So that means if you were not watching out for this is a good job that she did. She looked at what is my reference state, right? So you always want to keep that in mind. What is my reference state? So my reference state for this problem is 77. Now, this information is going to become very valuable as we look at the second part. So my second part says H4, 5, and 6 is at 60 Fahrenheit, right? So if we go back to our table, do we have 60 Fahrenheit? We don't have 60 Fahrenheit, right? What do we have though? We have 77 and 32, right? So what should we do? Interpolate, right? So I would pick, it's easy to pick 77 and 32 because the nice thing about this is 77 is also a reference state, so everything is 0 at that point, so at least one term goes to 0, right? So if you pick that, you have a much longer much shorter calculation to do, at least one thing short that you can deal with, okay? So I'll quickly show you this. I realize that this is not an exercise right now on your ability to calculate, so I want to show you what I did in terms of the details, and the work is already posted for you guys, and that's, that's Fahrenheit. Okay, and so what did I do? I just used the interpolation idea for all three of those values, and I got values for H4, H5, H6. Is that clear? Do you guys have any concerns up till here? Yes, no, maybe? Anything I should repeat? Sinking it in, do you want a minute to take a quick picture so you have it, or write it down? Or can I move forward? I would like some direction. Move forward, wait a minute. Okay. Okay, people who do not speak up, realize that people who do will then dominate the class space, okay? Agreed? Okay, all right. So now that we have done this part, so let's make the case that I have all of my H1, H2, H3, H4, H5, and H6 now calculated. So I had H1, H2, H3. I also will say that my H4 is negative 117.87. H5 is minus 148.84. H6 is minus 136.38. Are we done yet? Are we done yet? So what should we do next? We really need to calculate this term up here, right? So the way we are going to do this then is basically we'll calculate H out and out. So let's say just this part, H out. H out then becomes equal to 0.8 times H4, which is negative 117.87 plus 0.05, and guys, I forgot one thing, S2, 0.05 S2 times minus 148.84, and then plus minus 136.38 times 15, I believe, so that would be times 0.15 S2. So this whole thing, do you see, is in terms of S2? That just means that when you are working with the Q, it's per pound mole or some kind of mass. Yes? Okay. Similarly, for H1, we are going to do H in, we are going to do the same thing. For H in, it'll be 0.8 S1 times 8151 plus 0.05 S2, 12533. Do I have that right? I think so. Plus 0.15 S1 times 9831. So if you solve this, it turns out Q becomes equal to minus 122.195 S2 minus 8622.15 S1. So what do I do now? I have S1 and S2 that I don't have enough information to solve. Any thoughts? Can I argue that since nothing else is different, S1 equals S2? Yes? And that is some molar flow rate N dot? Yes? Because the number of moles that go in have to come out? Yeah? And therefore, I can say, okay, then this is nothing but Q over N equals minus 122.195 minus 8622.15, or this is equal to minus 8750. And the unit here is BTU per pound. MO. That is a lot of happy giggles. Okay, now, so what does that negative sign tell you? Exothermic heat was given off, right? Because you cooled down. Okay, so that makes sense as well that you lost that heat because it was given off. Is there any concerns with this problem? Yes. Okay, now I want to go back to a point that was raised, and that was, in this problem, what was the reference state? 77 degree Fahrenheit, okay, which was from the table. Now, what I will suggest is many times, if you can, life becomes a lot. Hey guys, for 2 minutes, I need your undivided attention. Everybody? Okay. What I would like to suggest now is that many times when you're doing these kind of problems, your life becomes really easy if you can pick one of the streams as your reference state. What do I mean by that? It's not zero, but I can pick any stream as a reference state, right? Because I am trying to calculate changes. Does that make sense? This is probably the most important part of the energy balance part of your lectures, is this idea that you can pick the reference state. Obviously, if you do this, then you can't use the chart, right? Because that chart had its own defined reference state. But you can use something else. And do you know what that something else is? That something else is, if you choose your own reference state, you can always pick T1, T2, Cp, dt. Because the Cp that you read off from the table is independent of the temperature. Okay, so now in this problem, my suggestion is we pick stream 1 as reference. If we pick stream 1 as reference, what we are saying is 1 atm and 1200 degree Fahrenheit is our reference state. Yes? What happens to H1? What happens to H2? What happens to H1? 0. What happens to H2? 0, right? Do you understand this? Yes, no, maybe. What happens to H3? Anybody who is not clear, this is a hard, at least I had a hard time grasping this concept or explaining this concept. So anybody wants this repeated or explained why? Yes, Ryan? You want it repeated and explained? Okay, so let me take a step back and do this again. Let's ignore everything else and focus on this term here. This is, you guys all know by now that this is equal to H, for that particular system, right? Yes? What is T1 and T2? It's just two temperatures, right? So can I say for H1, T1 becomes whatever reference state it is that we are working with, and T2 becomes the temperature we want to calculate the H at. Okay, so T1 is your reference state, and T2 is whatever the temperature we want to calculate this at, as opposed to picking 1260. Okay, you can't pick 1260 because this is H1. So we really want to focus on H1, which we know is at a temperature of 1200. Now, if we say that T1, which is the reference, is 1200, and T2 is also 1200, what is H? Delta T is 0. So this term is 0. Is that clear? The same goes for H2, H3, because they are all zeros, because they are all at 1200. So they are all at the reference state, which is the reason we chose that stream that was going in as our reference. So now we have reduced our calculation from 6 to 3. Okay, how do we calculate H4, H5, and H6? Are you okay? Hey guys, how do we calculate H5, H4, H5, and H6? Bodily functions, people. Bodily functions. Okay, yes. That's right. That's exactly right. We can still do CPDT, but now T1 is again going to be the reference, right? Because that's what we picked as our reference. And then T2 is whatever is this stream coming out. In this particular case, that's 1200, which is what we picked, because that was my stream going in. What do I do with CPs though? This is the part that is miserable. So I would only do this whole thing if I didn't have a stream table to read it off of. Okay? So where do I find CPs? Do you remember table 2, B2? I think we talked about this some time back. Yes? So we can go read off A, B, C, and D. I'll just give you one example. Carbon dioxide, which is on this page, so it makes life easier for us to, where is it? Carbon dioxide, see it says it's at the gas state. What was our carbon dioxide in? Gas state, so we are okay, right? And then, do you see it has 4 terms? A, B, C, and D. Yes? Similarly, you will have A, B, C, and D for nitrogen and water, which I have read off for you guys over here. Isn't that crazy though? You have to then read off A, B, C, and D for all 3 of them. And then, how do you calculate H? Remember, this formula always holds. H is just A times nothing plus B times T plus C times T squared plus D times T cubed dt, the whole thing integration. So we are not only doing, we are just doing stupid math. You see that? Yes. Yeah, so you know how mean I am? I start out out by saying take 4 terms, and then I realized no one's going to finish the exam, so then I tell you don't worry about 4 terms, just do 2 terms. Okay? So I will tell you in the exam how many terms. If I don't say anything, you will have to pick all 4 terms. Is this part clear? Yes? So there are 2 ways of calculating the H. The one is read-off table, the second one is this. Which one did you find easier? Read-off tables, right? But many a times we are mean, so we don't give you samples that are in that table of gases, or you have 2 different phases. That table is only for 1 phase. So if you have 2 different phases, then that table won't work, okay? So one reliable source always, whether you are here or back in industry calculating this stuff, is the CP table. It'll always work because you always have all the different phases listed as well. Okay. With that, I would like us to take a moment to breathe and reflect on what exactly did we learn from all of this. A minute.
Reflect on what we
Anybody?
learned.
Yes?
Learn to read the table.
Pretty easy way to do it if you have one phase and it's like all the same. But if it's multiple, it's a lot complicated.
Right. So what I'm trying to get at is when you have one phase, then it's pretty easy to just read everything off from one table, right? And in such cases, this setup that I showed you, even if you do this setup, you still end up doing a lot of calculations. But most of the time, I will probably combine this with the spray chamber problem, right? Because I also want to test you on Raoult's law, or a humidifier problem, or a reaction, right? And so I can guarantee you for the final exam, you have only 2 problems. One tests you on Raoult's law, one tests you on your ability to do material and energy balance on equations. And in the process, also remember to deal with ideal gases and non-ideal gases, calculations of C, right? So how do I combine all of those things into a couple of problems and make sure that when ABET comes to question me, I did ask for complex problems and looked at your ability to solve those complex problems, right? So we have to combine all of those things. So let's do it in steps. The first step is, let's still assume there is no reaction and wait for December 2nd to talk about reactions. But let's at least talk about phase changes. So no reactions, but phase changes. What do I want you to remember? I want you to remember that when you calculate enthalpy changes, when there is a phase change that occurs, that enthalpy change will be very different from just a temperature change. I also want you to remember that the best bet is to be able to develop your own process paths. I will stop here and ask you, what is a process path? Do you guys remember what is a process path? What's that? How do we go from A to B, right? And we said for enthalpy process paths, you can have hypothetical process paths. Do you remember that? Yes? So for phase changes, those hypothetical process paths are your best friends. Okay? So, one of the big changes that you will then think about when you have a phase change is what? When you have a phase change, what happens in terms of enthalpy? When you have a phase change, what happens in terms of enthalpy? Okay, I will go back to my question. Why is steam at 100 degree hotter than water at 100 degree? Because the energy needed to change water into steam is a lot more. So when you have steam, it also has the latent heat of vaporization. Do you guys remember from physics? That latent heat of vaporization, or that latent heat when you have a phase change, plays an important, significant role in these calculations. So what I want you to understand is anytime you have a phase change, you should think of that latent heat. What kind of latent heats do you have? Anyone remember? Come on guys, what kind of latent heats can you have? Okay, there can be sublimation, there can be vaporization, fusion, right? You can have a change from solid to liquid, liquid to solid. You can have a change from liquid to vapor, vapor to liquid. So those are the only kind, and then you can have sublimation. So those are the only kinds of latent heat you will have. But what I want you to understand is this latent heat is going to be way more than sensible heat. Now, someone quickly remind me, what is sensible heat? What did we just calculate in the previous problem that we were working on? Yes?
Sensible heat is the amount of heat that must be transferred to raise or lower the temperature.
That's right. So it's just the Cp delta T, right? So sensible heat usually turns out to be much smaller than the latent heat. Okay, so keep that in mind as well. Sensible heat is usually much smaller. And also keep in mind, sensible heat is for the same phase. It's a single phase. But latent heat is when you have a phase transition. Okay, great. So then you guys already told me, you know that there can be either fusion, latent heat of fusion or melting, and latent heat of vaporization, or in this case it is condensation. But what I want you to realize is the sign becomes important as well. So if you go from solid to liquid, the heat is positive. But if you go from liquid to solid, the heat is negative. Okay? Similarly, if you go from liquid to vapor, the heat is positive because you actually need a lot of extra heat to go from that liquid to vapor phase. But if you're going from vapor to liquid, it is negative. And the best way to show this, I am a visual learner, so I like to look at graphs. And to me, the best way to show this is using a chart of delta H versus T. So if you look at delta H versus T, do you see that from T1 to T2, I have a small curve. There's a small change in delta H, and that can be given by T1 to T2 Cp delta T. What heat is this? What is this part? This part of the heat, what is it? Sensible heat. That's right. So this part of the heat is sensible heat.